A lot of engineers are overly paranoid that their design is not going to work. And this can cause paralysis by analysis or just ungodly amounts of testing, which will slow you down and is usually tedious. So there's a few ways to work around this problem. What we're going to show today is a very, very old resistor. And by looking at these older designs and components and seeing what ye olde engineers had to deal with, we can get an appreciation for it. And we can realize that for a modern day design, it actually takes a lot to break it. So in your just normal resistor right here, so you'll notice tolerance is probably going to be 1%. That's what I always choose just because it's cheap. Temperature coefficient is 100 ppm. So I talked about this in my last video. But just as a refresher, ppm is this yellow line right here, which you'll see at 100. So at the edge, you're plus or minus 1%. And that's in addition to the stated tolerance. So 1% plus this 1%, plus or minus 2%. I want you to keep that in mind as I'm going through this ye olde component. Plus or minus 2. So right off the bat, so of course, 50-year-old technology is going to be through hole. So surface mount wasn't around back in those days, I don't think. So right off the bat, right here, see tolerances. So 1% is our cheap stuff. Back in their day, probably would have been 5, 10, 20? Like, holy moly, I would have to think real hard this day and age to how I could implement a 20% resistor. Maybe a pull up or a pull down resistor, or maybe something that's like really low value, like a termination resistor. But other than that, no, I'd have to really think about how to get this type of tolerance in there. I'd have to design around it. So we're going to go through some other specs. Voltage ratings, this is about what you'd see for modern. We'll skip past some of this stuff. So, all right. So one thing I want to look at here is load life. 1,000 hours at 70 degrees ambient and permanent resistance change. So you'll see a maximum and typical. Guys, whenever I look at a data sheet, I do not care about typical. I design for maximum. I want my circuit to work all the time at all tolerances per data sheet. So +4, -6. Now, if you look in these modern data sheets, they'll still have all this stuff. Or at least this one from Vishay does. They'll talk about the tests, all the standards they use. And if you look right here, endurance rate at 70 degrees, they use the same spec. So this is one of the good things of never changing stuff. Now I've got an apples to apples comparison between modern and ancient. So plus or minus 1% plus a little tiny bit. So, which completely annihilates this spec right here. So some of these other ones here, terminal strength, effective solder heat, vibration shock, yeah, they're in here too. Overload. So I'm not going to go through them. Vibration. Yeah, so modern's going to be better, but it's not such a huge night and day difference. But what is moisture resistance? If you look at their spec right here, so 10 days, 40 degrees C and 90% humidity. So steady state. So you look at this. This is incredible. Okay, so it's always going to be -0. That's just how it is with this technology. But up to plus 15%. This is for 1/8 watt, quarter, and half watt. Over 10%. Good Lord. And this is a temporary thing. So if you're using this outdoors, Lord have mercy on your soul. So, and you're just like, okay, what is modern? Here, we'll search for it. Moisture. It's not even in here. There's no spec for it. The only thing you can get a spec is for all these compliance testing stuff, somewhere between 25 and 75%. So, as you would expect, your regular surface mount, they do not care about humidity. But these ye olde ones, carbon composite, massive difference. Absolutely massive difference. And then look at the temperature characteristics of this. So they say ambient down here, but normally when we measure temperature, it's from the surface of the resistor. So not quite sure what's going on there. But look, we said it was plus or minus 1% on a modern day resistor. Look, this is 6% right there. That's for a 10 meg resistor. This varies upon the resistance. But we can still get, 3 to 6, a little bit less on the high end. Notice how this goes to 105. See? Meanwhile, a normal resistor will go to like 125. So, okay, all right. So we've got a better temperature spec for modern. Cool. Look at this. Oh, an incredibly nonlinear. Like a parabola. Meanwhile, this linear. So another word for linear is easy to calculate. So one thing that is about the same though is derating with respect to ambient temperature. So you'll see in a modern one that it's 70 degrees C is when they start derating it. So by that, percent of rated watts that you can still do. So yeah, this line here actually hasn't changed in decades. So that's how we still design resistors, I guess. So now what I want to do is just kind of add up all this stuff. So in the modern resistor, we said plus or minus 2%. So we're going to assume 20% tolerance on this thing. Let's just add 5. Just keep the numbers right. 25% plus another 15%. So we're already at plus 40%. So then here, plus 44%. So, and then on the low end, because of that humidity, 44 minus 15. So almost minus 20 to plus 45%. So what in the world? This component is complete garbage compared to what we use this day and age. But remember, engineers of that day and age still made it work. So they would have to design around this. So a lot of older things need calibration. So you'd have to do it a lot more often. You'd have to design with this in mind. A lot of older designs also had potentiometers everywhere. So that's part of calibration that you would have to do. So my whole point of showing you this is that, hey, if they can make this work, then what you have to work with this day and age is so much better. In a modern design, it actually takes a lot to ruin it. So, guys, you can put the paranoia aside. What you're dealing with is just so much better. And this is just one component. Other components are also so much better. We haven't even begun to talk about modern day layouts and how they completely annihilate what they would have done back in the day. I mean, just think about it. All components back in the day, through-hole designs, and 4-layer was expensive. So it'd be through-hole components everywhere, plus a 2-layer board. Because of all the holes you're making, because of through-hole, you won't be able to have such an easy time routing. So have no fear when you're doing a modern design. Chances are it's gonna work. So that's what I'm gonna leave you with today. So like, subscribe, all that normal stuff if you enjoyed the video. Comment. So thank you for your time. Have a good one.